Hello. Today we're going to be talking about liquid and vapor equilibrium, specifically those relating to Raoult's law. Now, to start off, we have to discuss what is Raoult's law. Now, Raoult's law is the idea that pressures can be subdivided, and pressures as well as vapor pressures and things such as those, can be subdivided from the total pressure into smaller component-based specific pressures. For example, from Raoult's law, we get the idea that a pressure, P total, can be equal to the individual molar components in vapor. So for example, if you have two mixtures, mixture of A and B, the total mole fraction of A times the total pressure will give you actually the specific pressure, which is the pressure exerted by that specific portion of the total pressure by that one specific substance in the mixture. Now, we also, because of Raoult's law, define the idea that the liquid composition comes into effect as well. For a liquid mole fraction, X of I, if you multiply that by the pressure of saturation, which is Pi saturation, which is also a function of temperature, thanks to things like the Antoine equation, we have a three-part Raoult's law. Now, this Raoult's law equates the specific pressure of a substance, again, the pressure that is exerted by that one substance in the mixture, which is, again, defined right here as the substance's mole fraction in vapor times the total pressure of a container, and that is related to the liquid composition. And that's, of course, very important for a liquid and vapor equilibrium state, where we have a container that contains liquid that is composed of X1 and X2 substances that we want to bring to we want to have vapor present. So, to start off, we have to start discussing four topics. We have the due pressure, the due temperature, and the bubble pressure and the bubble temperature. And what those means are as follows. For the bubble set, we want to know if we lock the temperature at a certain point, at what pressure will we get the first bubble of vapor? Now, the bubble will be composed both of X1 and X2, as our liquid is a mixture of both. However, the composition of the liquid will not be the same as the composition of the vapor. Similarly, with bubble pressure, bubble temperature is saying if we lock the pressure and we vary the temperature, at what temperature will that first bubble of vapor appear? Now, the easiest one to do for order and clarification, because we'll come around to the dues in a second after we kind of run through these, because doing the bubble set first is more conducive to doing the due set later. To start, we're going to look at the bubble pressure, because it's easiest to do given the temperature to get the pressure. Now, looking at this equation right here, again, since this relates the pressure and temperature as well as the liquid here and vapor mole compositions, it's quite easy to arrange those in a way so that we can actually derive the bubble temperature, pressure, and the due pressure and temperature. So, looking at this system right here, since we're talking about bubble pressure, we are going to lock in the temperature. This is locked. I'll draw a little lock here. There we go. We've locked in our temperature. So the question is, at what pressure will we observe our first bubble forming? So, how do we solve for that? Well, because we know right here the definition of the partial pressure is the vapor mole fraction, which we don't have, because again, we're only given the composition of the liquid. But we know that this right here, the vapor times the total pressure, is equal to the liquid composition times the saturation pressure. We can actually use this relationship right here between pressure and temperature by the liquid and vapor in order to actually solve for our bubble pressure. Our bubble pressure. I always get them mixed up since bubble pressure and bubble temperature both have bubble as the same as the first word, so it gets a little hazy sometimes. So when we look at this, we say, well, the definition of the bubble pressure or bubble temperature, either way, is when the first bubble forms, correct? Which means we want to bring each of these substances independently to a boil. Because when you think about a single component mixture, a mixture that has one thing in it, obviously that will boil when you heat it up or increase the pressure to a point where the vapor pressure equals the external temperature, and that will allow liquid to go to vapor and vice versa. That will create a vapor-liquid equilibrium. But when we have multiple components in our mixture, we no longer are boiling, because the boiling point of this mixture no longer is something that can be determined by a single mixture in isolation, by a single component in isolation. It's a result of the mixture in total. So when we look at this, we can no longer say, well, the boiling point of this one is 30 degrees and this one's 50, and it's half and half, so it must be 40 degrees. It's a bit more complicated than that. And that complication comes in from this multiplication right here, because at the bubbling temperature or pressure, the first bubble forms when each component is satisfied its saturation pressure when discounted by its liquid composition. So we want to find out when the pressure is equal to, because this is the definition of producing vapor or boiling in a single component mixture, and obviously the multiple component analog would be bubbling, the total pressure is equal to the sum of each individual vapor pressure. Again, the vapor pressure of each, or not the vapor pressure, the partial pressure of each component is equal to the total pressure exhibited in the system. That would be when bubbling would occur. And now, because we can see right here, Raoult's laws of equivalence right here tell us that this is exactly the same as the sum of each component is mole fraction in the mixture multiplied by their saturation pressure, which is again a function of temperature. So this right here, skipping this intermediate step right here, which is just, this is the definition of to boil, would be the total pressure of the surroundings equal to the pressure, the sum of the pressures caused by each internal component in the mixture, which we then equate to, using Rhodes Law, the liquid mole fractions and the saturation pressure at a certain temperature T. So using this, we can directly connect the pressure as to solve using the temperature that we're given. And this right here would be our bubble pressure. I will circle this, because this is our bubble pressure. Now that's essentially just a consequence of Rhodes Law, this equality right here and the definition of what it means to bubble. Now, to do this in reverse is a bit more complicated, because to find the bubble temperature, we would instead, if I erase this with my finger real quick, we would instead lock in our pressure and say, for what temperature at a certain pressure will the first bubble again form? Now, this is essentially the same equation, except instead of solving it linearly, where we plug in the temperature, use the mole fraction of the liquid that we're given, in calculating the vapor pressure with that temperature, and then adding them all together to find the pressure at which everything works out and our first bubble forms, we're doing it in reverse. We have the pressure at which our bubble is going to form, or we want it to form because it's locked in, and we know this still. We still know the liquid mole fraction composition. However, we don't know what these are as a result of not knowing the temperature. So this is something that we would, in Python or in mathematics, we would use a root solver to basically figure out for what temperature do we get this value out. But it is essentially the exact same equation. If we were to rewrite it, we would say that if we were to take that, so this is a sum of each thing. And I guess I should notate, since we don't actually need to worry specifically if we have two mixtures, we have three, we have four components. It doesn't matter how many components are in this mixture. So this, I could amend this to be a summation from n is equal to 1 to capital N, where capital N is the number of components in our mixture. Now, to look at bubble temperature, again, it would be taking the summation and essentially pulling these all out. If we were to expand this and written as x1 plus x1 times P1 saturation at point T, and essentially we'd want to decompose this and figure out for what single temperature we would equal a certain pressure, which again, you could write it out that way, but it's essentially the same as this. It's just, it'd be on the opposite sides. So I don't really see a point in doing that, because for illustrative purposes, the relationship between P and T is exactly the same, and all we're doing is kind of inverting how it works. Now, the question becomes then, if this is our bubble pressure plus our bubble temperature, I'll abbreviate it as temp just to save some of your time and my time, how do we figure out the opposite? Instead of having a liquid right here, where we're wanting to find a single first bubble, what if instead we had a container of vapor, hotter and at lower pressures than before, so it's nebulously floating around, I'll do this to indicate it's a vapor, of x1, x2, x3, yada, 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 as many components as we want in this vapor. I'll write all vapor here too, just to really clue us in that we're here now dealing with vapor. Now again, this comes from Rhodes Law and the consequences of the definition of what it would mean to do. Again, the single component equivalent of do would be to condense. But again, condensing implies that it's working off of a single concrete boiling point of a substance. Because we're using a mixture and we have multiple substances, each with their own boiling point and volatility and saturation pressure and all of those variables that come along with and properties of independent substances, we can no longer call it condensing and boiling. It is bubbling and a dew point. So, since we have all vapor, we now need to worry about coming in reverse and when would we form the first droplet of liquid, and of course, what would those mixtures be? Now, because we're dealing with a vapor, we no longer have our liquid composition xi. Instead, we have yi, which is our vapor composition of each substance. So, in order to do this, we have to start with something that seems a bit tangential, though obviously true, and that would be the definition of, again, when that first liquid drop forms, and again, I'll switch this back around because we're going to be looking at temperature first, and then from temperature, or from pressure, because pressure is the one we're looking for. Given a temperature and wanting to find a pressure at which the first drop forms, how we would describe the first drop is actually the key in order to solving the dew pressure and temperature. So, because this first drop will form, however many substances we have, we know that the mole fraction of every single one of those substances in this liquid first drop is going to be equal to 1, right? I mean, that's the definition of the mole fractions, is that, obviously of all the water, or of all the, not water, of all the liquid that forms, all of it must have come from the substances that are in the vapor here because it's a closed box. And so it couldn't be anything else. So when we start with this, we simply say the sum from n is equal to 1 to n of x to the I. So the sum of all of the liquid that forms, the sum of all the partial, the liquid mole fractions in this first formation droplet in our dew pressure temperature system, our situation here, has to be equal to 1, because that's the definition of a mole fraction, is that it divides everything that's there up into its component substances. So, when we look at this and we use Raoult's law and say, hey, we know that the vapor composition, the vapor mole fractions, are correlated to the liquid mole fractions, and we actually can rewrite this as such. Well, if we want to, we have xi here, and that's in our definition of what a mole fraction is in liquid, but we don't have any of that information. All we have is the vapor mole composition information. So because they're correlated to each other through the total pressure and this, which is again a function of T, the saturation pressure, we can actually rewrite this as xi is equal to yi total over pressure of each individual substance, the saturation pressure of each substance base as a function of T. And because of this equality, which again is a direct derivative of Raoult's law, all we did was divide by the pressure of saturation of each substance as a function of T, we can actually plug this in to that formula we just found. Again, this is the definition of a mole fraction. In liquid or in gas, it doesn't really matter, but for liquid, because we're talking about going from vapor to liquid, when we substitute that in, we get the sum of n is equal to 1 of n of yi, which is again the vapor mole fraction, times the total pressure of the system, which is what we're looking for, and pi saturation, so the saturation of each component, vapor pressure as a function of temperature, is equal to 1. And now we can do some very simple algebra by saying, well, obviously this, the mole composition, and the saturation pressure depend on each substance, but the total pressure is the total pressure. And since we're multiplying those together and then summing them all up, what we can do is just pull this constant, because in our case, even though we don't know what it is, we know the pressure at which the first dewdrop forms will be a constant. We can just pull that out of our sum. So we have our sum from n is equal to 1 to capital N, which again is the number of components in our mixture, is equal to yi over pi sat as a function of T, that mole fraction in the vapor, over the saturation pressure of each substance as a function of temperature is equal to 1. And now all we have to do is divide this over to find our pressure. So our P, and I'll call this dew, is equal to 1 over the sum. I'm going to leave out the bounds just to make it a bit more. I'll put them in. N from n is equal to 1. I just want to make sure this is all visible on camera. Of the vapor mole fraction over the saturation pressure of each substance as a function of T. And this right here is our dew pressure. Now, again, when we try to look at dew, pardon me, Easter did a real number on my throat. The dew pressure right here, as described, again, when we want to go back and switch it to say, instead of knowing our temperature and trying to find our pressure, we want to find our temperature knowing our pressure. How do we go about this? Well, just as with here, which I'm going to say P of bubble, B-U-B, just to make sure that's clear. And all these little things that are seemingly not important, but are very important because they're a part of the notation, and of course notation is super important. If we switch this around, we have the same thing over here. We have the same, like a repeat of the situation before, where it's the same relationship, it's just looking at it from the opposite end. Instead of plugging in the same T to a bunch of component saturation functions, saturation pressure functions, and spitting out the pressure, and now, we have the pressure and want to find what the T is for all of those functions. It's the same here. Instead of knowing the temperature that we plug into all of the different components, saturation pressure functions, and finding the pressure, it's the other way around. We have this, and we want to find what T in all of this, throughout this summation, will give us the pressure that we're locked in at. So for this one, rewriting it actually does benefit us quite a bit, just it makes it a little easier to see since this is on the bottom of the fraction. If we rewrite this, kind of like imagine reverting back to this step temporarily by just remultiplying over, and since we know this, and we're looking for this, it's actually quite a bit easier if you were to rewrite this as y of I. Actually, I'm kind of writing this. I don't want to step in front of the camera, but it's kind of hard for me to write from the left side with my right hand, so I guess I'll just get down on one knee to write this. If we say that yi, the vapor component of each substance, divided by the saturation pressure of each substance at the sum from 1 to n, minus, now all we're going to do is divide this P over and then subtract everything, minus the inverse of the pressure is equal to 0. We now have something that's prime and ready to be put into some kind of root solver function in Python, like we're going to do later, or using a mathematical graph of some kind to find the zeros of the function. We have something where, knowing this, because again, this is what we're locked in at, we know the vapor composition, and we're looking for this, we can figure out for what input T this is equal to 0. So this will be really good for our T.
At this moment, my phone failed and the recording was cut off prematurely. Thankfully, the only thing we missed was me going over what we'd already previously discussed throughout the course of this video, so no major information was lost. Unfortunately, these technical difficulties, and others like it, will continue throughout this homework because, for some reason, Luck has decided that this will be the homework of technical horrors.